So in this webinar, we will show some measurements that were collected in the fall of 2019. Those measurements were conducted in the Waddenzee, which is a shallow estuary in the northern part of the Netherlands, which is connected to the North Sea by tidal inlets in between barrier islands. The focus area here is between the mainland and the island of Ameland. This whole area in between the island and the mainland is submerged by seawater during high tide, and during low tide only the main channels remain with water. The area is highly dynamic due to very large flow velocities, and therefore it's really challenging to keep the main navigational channel for the ferry that goes to the island, here in the dashed red line, to keep it open. Here you can see two ferries passing each other in a very narrow navigational channel during low tide. Dredging in this area is continuously needed to keep the navigational channel open. And recently, a shortcut was constructed. You can see here, this part was, there was a shortcut was dredged to reduce the time for the ferry to go between the mainland and the island. And the measurements presented here were done to compare with a similar campaign before this shortcut was constructed, to be able to see what differences did it make in hydrodynamics and morphodynamics in this area. You can see here an overview of all the activities that were part of this large campaign. So what you see, this is again the meander band that was dredged. So here you can see the shortcut in the navigational channel. In yellow, the yellow locations indicate where soil samples were taken from the seabed. In the red, there are two locations where we had bottom frames, where flow velocities and sediment concentrations were measured over the full 5-week period of the campaign. Then in green, there are 4 locations where vertical profiles were measured of sediment concentration and velocities during 13 hours. I will get to that in a later slide. And then we did also discharge measurements on the purple transects. So to illustrate how dynamic this area is, I show here the differences between 5 morphodynamic surveys that were done in the first half of 2019. And you can see here in red deposition and in blue erosion of the channel, and yeah, the numbers are in meters per month. And you can see that they are up to 1 meter per month. And what you actually see is that this meander band is migrating southward, and therefore there is deposition in the inner band and erosion in the outer band. So this illustrates how dynamic the navigational channel is, and how difficult it is to keep a good navigational channel for the ferry. To illustrate some of the measurements we did that are relevant to the results that Maeve will later present, you can see here at location A, so in this meander band, we deployed a bottom rig for 5 weeks, so for a full campaign. And you can see that there was a Nortek ADCP, the Signature 1000, installed on the frame, and it was co-located with an OBS to measure sediment concentrations at 1 meter above the bed. Now, to illustrate how results from this frame looks like, we have here on the vertical axis the height, on the horizontal axis the time, and you can see the flow velocities from blue to red, and with red is the flood tide. Yeah, you can see flow velocities up to here during spring tide, 1.5 meters per second in this on this location. And then sediment concentrations at 1 meter above the bed show that with each low tide you have an increase in your sediment concentration due to the higher velocities. Sediment concentrations are up to around 4,000, 6,000 milligrams per liter. Maeve will later go into more detailed analysis of those velocities. And then we did discharge measurements. we measure discharge over the full tidal cycle. So for 13 hours, we sail twice an hour each transect. We did that with the Nortek VM system. For everyone who followed the webinar yesterday or on Wednesday, it was explained how this system works. So basically, we have a downward-looking ADCP deployed on the vessel, and then we, twice an hour, we sail all those transects for 13 hours straight. So then you get over the full tidal cycle your flow velocities over the channel. This is an example of how that looks, how the user interface looks on board of the vessel. Then on 4 locations, we did measurements with a so-called measurement fish. So this is a device which includes a lot of different instruments, which we lower twice an hour. Also for a 13-hour period, we lower it into the water column towards the bed, and then you get flow velocity, sediment concentrations, at different heights above the bed. The nice thing is that there was also we could also take sediments or water samples, so we can also analyze the how much sediment is in the water and use those concentrations to calibrate the OBSs. Those measurements were done in combination with the vessel-mounted ADCP to be able to compare measurements from the ADCP with the fish measurements. To show an example, here you can see on the left velocities, so height above the bed on the vertical, and then velocity on the horizontal axis. And you can see that now, depending on the water depth, here it's 2 to 3 meters deep. You have 3 to 4 points in the vertical of your velocity, and on the right, plots of the sediment concentration. Now we teamed up with Nortek to be able to compare the conventional methods we use with new techniques to be able to see whether in the future those measurements can be done more efficiently, more detailed, more accurate. And the main focus now was on the echosounder that's included in the ADCP. And Maeve will tell you how it works and how the results look.
Hi, thanks, Joost. Echograms provide vast temporal and spatial access to geomorphic and biological features, but pairing them with ADCP velocity data allows for flux calculations and trajectories. But ADCPs were designed to optimize velocity measurements, and this has left us with echograms with low resolution, limited dynamic range, and data gaps near the boundaries due to side lobe effects. And these are characteristic of all commercially available ADCPs. So Nortek's Signature 1000 vessel-mounted ADCP was designed to address these limitations. It uses a 5th vertical single beam echosounder that occupies dedicated pings within the velocity data stream. So now both the velocity and echosounder measurements can be optimized. So now in theory, we can see the boundary with a vertical beam, but in practice, the seabed is going to be a blind spot for vessel-mounted ADCPs, and the sea surface will be a blind spot for bottom-mounted ADCPs. And this is due to mounting and blanking distances. But if we combine data from 2 instruments, then we can see to both boundaries. So to test the success of this technology, Nortek teamed with Waterproof, and now we're going to look at some of the data from the measurement campaigns that Joost described. So from the vessel-mounted deployment, we'll be looking at echosounder data. The echosounder was set to pulse compression with a 5-centimeter cell size, a 2 Hertz sampling rate, and the return signal was corrected for losses. So we'll look at relative volume backscatter. So this is the suspended sediment concentration plot. Here we have depth on the vertical axis, time on the horizontal axis. This is about a 13-hour period. And mud suspended sediment concentration in milligrams per liter in the color bar. And so you can see in this example, the higher concentrations reside near the bed. On the next slide, we'll be zooming in on this 30-minute window right here. So again, we've got depth versus time, and in the color bar, relative volume backscatter. And so you can see this really high resolution data right down to the bed. And you can also see that the high intensities are located in this band right above the bed, consistent with concentrations that we saw in the previous slide. So next we'll look at data from the bottom mounted deployment, where the cell sizes were 25 centimeters, a little bit bigger, and we'll see a 10-day subset. So this is the echogram. We've got range on the vertical, and this starts at about 1.5 meters. This bottom 1.5 meters is clipped out because this is where the instrument sits and its blanking distance. Then on the horizontal, we have time, and in the color bar, we have relative volume backscatter. So we'll be coming back to this image. Here we have velocity. So again, range versus time. And then we've got velocity in the color bar. And so this slide is key to understanding the following 8 slides if you're not used to looking at tidal data. So from the instrument's perspective, the flood tide is coming in, and we assign that a positive velocity with a maximum of about 1.2 meters per second. And then with the ebb tide, the flow moves away from the instrument, and we assign that a negative velocity with a minimum of minus 1.2. And then the zero velocity is just about light green. So I'm going to run through the tide cycle, and where we are in the tide cycle will be indicated with these thin vertical lines. And here we're just talking about tidal forcing. We're ignoring any other mechanisms that might be present. So at the onset of the flood tide, the pressure gradient from ocean to land is at its greatest. So the velocity is heightened as water from sea rushes landward. And we can see that in the velocity in these thin red bands representing 1 to 1.2 meters per second. Then during the flood tide, velocity decreases towards a minimum, and this occurs in the transition with these lighter colors. And then during the ebb tide, we have increasing velocity as inland waters drain over the mud flats to the sea. At the end of the ebb, we have another maximum velocity period, minus 1.2, shown in these dark vertical blue bands. And then in the transition from ebb to flood, we have another minimum shown by these very thin pale stripes. So the ebb's increased energy can stir up mudflat sediment, and the relaxation of this energy in this transition allows the sediment to be released back into the water column and towards the seabed. So now we'll look at the echograms. So during the flood tide, we see the lower intensities that represent relatively dilute seawater. And during the transition from flood to ebb, these low intensities remain. And then during the ebb cycle, we've got increasing energy over the mudflats. So we see a lingering low intensity from the ocean water and the onset of enhanced intensity. Then these intensities increase through the ebb cycle to the transition. And you can see these pockets of high intensity value at the sea surface at low tide. And then the cycle begins again with ocean water rushing in. So this coupled velocity echogram time series allows us to see where intensity extremes reside, under what conditions, and for how long. So now we'll look at the echograms that we've already viewed from both the bottom mounted and the vessel mounted instruments. So the top one is much longer, it's the 10-day time series, and the bottom 30-minute data set occupies the period represented by this thin line. And here I've just adjusted the color bar of the bottom image to match the extent of the top. So you can see that the bottom mounted ADCP provides sea surface data that's missing in this bottom image. And the vessel mounted ADCP provides data near the seabed that's missing in the top image. So this bottom 1.5 meters that gets clipped out. So if you were performing sediment flux calculations, these two images would give you a complete picture. And this bottom and vessel mounted ADCP pair really is ideal. As this example shows, we've got these high intensity values at the bed that we wouldn't want to leave out, and these pockets of high intensity up at the sea surface.